we want to try and stay as much on time as possible. So with that, I'm going to say good day to everyone and introduce myself. I'm Julio Ibarra, the principal investigator of the AmLite Express and Protect project. And I'd like to welcome you all to the 2022 South American African Astronomy Coordination Committee meeting. So I'll start us off with a brief introduction to the SAC and make some introductions as well about the project. So let's see here. Okay, so we have a new name now for the SAC. We added Africa to the project name. So it's now South American African Astronomy Coordinating Committee. This was suggested to enhance the name of the SAC to include Africa, and also for consistency with the name of the AmLite project, which also includes Africa. The new abbreviation is SA3CC, and it's pronounced SAC just as before. So SAC will include astronomy projects in South Africa and explores the use of the AmLite SACS link, which is a South Atlantic submarine cable system that connects from South America to Africa. So it's connecting Africa, South America, and the US. Today we have an update on the Meerkat project, and tomorrow we will have an update on the National Research and Education Network of South Africa, SANREN Tenet. We also have a new co-chair. So I would like to say a few words about our new co-chair, Dr. Robert Bob Blum. Bob has been attending the SAC meeting for I think a few years. Bob is Director of Operations for the Reuben Observatory. So Bob has been with NOAO and NORLAB since 1997, starting as a support astronomer at CTIO. After almost 10 years in Chile, he moved to Tucson, where he works on other aspects of NOAO and NORLAB's program. He was deputy director for 10 years and then moved over to lead the development of the Reuben Observatory operations plan and team. He's committed to making Reuben a success, including for our community in Chile and South America. And when he's not doing astronomy, he loves to spend time with his family and doing anything in the mountains. So welcome, Bob. Would you like to say a few words to the SAC?
Thanks, Julio. It's great to be here. It's my honor to take over for Jeff Cantor, who from Reuben Observatory co-led the SAC with Julio for many years, and Jeff is now retired after long and dedicated service to this group and to Reuben, and I think to the overall network initiative generally. And so I'm happy to take over and be with you here this week and in the future. So I'm looking forward to a good meeting. So thank you very much and welcome everybody.
Thanks, Bob. Okay, some information about the SAC and why we're here. So first, it's my privilege to announce that the SAC is now in its 11th year. And so SAC brings together two synergistic communities: the astronomy projects, operating observatories in South America and South Africa, and also the research and education network operators in South America, Africa, and the US. The SAC community is growing. There were 61 attendees at the 2021 SAC meeting last year. Some information here about the goals of the SAC. It's to provide input and advice to AmLite and research and education network operators on program and network needs. Our meeting and community serves as a venue for coordinating network requirements of the astronomy projects and institutions. The SAC aims to help the projects improve their resource planning and operations requirements of distant facilities and users in South America, South Africa, and the US. So for projects reporting today that are under construction, please inform us of your network requirements. Let us know how we can help you. For those projects that are operating, please inform us of any changes in your network requirements. Your updates are very important. They provide input to the SAC meeting report. So everything that we're going over today and throughout the year, we do consolidate that in a report that then goes to well, the community and also the NSF. So AmLite succeeds because of its partnerships. AmLite interconnects the US to key aggregation points in South and Central America, to Africa. We have landings in Brazil, Chile, Panama, and Cape Town. The AmLite Express and Protect project is a 5-year award from the US National Science Foundation to Florida International University, USC Information Sciences Institute, and Vanderbilt University. Cooperative and collaborative partnerships allow us to succeed. We have partnerships with the Research and Education Network of the state of Sao Paulo, REDNESP, RNP, the National Research Network of Brazil, CLARA, the Regional Research and Education Network for Latin America, REUNA, the National Research and Education Network for Chile, AURA, Association of Universities for Research in Astronomy, the Vera Reuben Observatory, Flora Lambda Rail, and Internet 2. Some points here about the 2021 SAC report. It's available on the AmLite project website at the URL that's on the screen there. I want to thank everyone who contributed to the report. And I also want to thank the 2021 SAC Program Committee. And a big thanks to Dr. Vasilka Chagorova for leadership and writing the report. So you can download the report. It's online at the link there in this slide. And we can also make the link available to you in the chat. And just some words about the SAC participant guide for logistics here. So everyone who registered should have received an email with a link to the 2022 SAC participant guide. This guide provides a one-stop point of reference for all links and materials you will need for the meeting. If you did not receive a link to the guide, please let us know in the chat. Please be mindful of your presentation time limits. We want to try and stay on time with the agenda. During a presentation, please write your questions or comments into the Zoom chats. We will answer questions in the chat also during 5 minutes of the Q&A after each presentation and during open discussion period. The meeting agenda is also available online at the following URL. And thank you all for taking the time in your busy schedules to participate, all the presenters and attendees. I want to give a thanks to the program committee, to Bob Blum, Vasilka Chagorova, and Heidi Morgan, and also to Vasilka for coordinating the logistics and many details of today's meeting. So with that, I would like to stop sharing my screen and turn the meeting over to, I think, Bob, you're the first speaker, you and Christian, if I'm not mistaken.
Let me fire up here. Here we go. Okay, yeah, let's get started. So let me give you a brief overview of Reuben Observatory. I'll start with some high-level things and give you a little refresher about what we're all about for those that may be first-timers or have forgotten some of the things about what Reuben's trying to do. And then I'll give you a brief update on the status of the project and where we're at coming out of the pandemic and how that's been going. This is a joint effort by myself and Christian Silva. So Christian has taken over the duties at Reuben Observatory in La Serena and Cerro Pachon, where we're located, from Jeff Cantor on the overall network project and building up the network infrastructure to get us ready for operations. And glad to have Christian here. There's a few other Reuben folks here. Richard Dubois I know is here. And some others from SLAC and the DOE sphere, and we'll get to them later on in the meeting. So let's just get into it. I wanted to remind you of what our vision and mission are, which kind of drive everything we're doing and really set the stage for the science, the program, the system, which includes the network, of course, and this big data science project. So by acquiring, processing, and making available the vast data set collected with the Vera C. Reuben Observatory, the legacy survey of space and time will provide the community with the data to address some of the most fundamental questions in astrophysics, advance our field of astronomy, and engage the public in the discovery process. So as we've changed our name to Vera C. Reuben Observatory, we've kept LSST in the sense that that's what we're calling the 10-year survey that we're about to embark on. Our mission then, following from that vision, is to produce an unprecedented astronomical data set for studies of the deep and dynamic universe, make the data widely accessible to a diverse community of scientists, and engage the public to explore the universe with us. And of course, the long-haul networks are key to being able to do this, in particular, this aspect of the dynamic universe, where we need to get the data up to our data facility in California on minute timescales as we take data all over the sky every night for 10 years. So this vision and mission support our science priorities, which are really driven by our community, including all of you, our folks, our community in Chile, our other international partners, of course, everyone in the United States and elsewhere in Latin America. And we have people in South Africa, as well as other European and Asian scientists coming in to join the overall Reuben enterprise. So we will produce this unprecedented optical survey, what we call the legacy survey of space and time. Its depth and breadth and the time domain axis that it includes will be indispensable in delivering on the science priorities of this global community. Right now, the operations team is being set up. We're growing year by year as we approach operations, and we really have a single-minded focus on preparing for operations and delivering the data products to the community. That includes data previews and data releases, and I'll talk a little bit more about what I mean by data previews later on. And it certainly includes all the effort to build up the network infrastructure and make sure that's ready as we get through commissioning and into operations. Just a reminder that everything we're doing and building is really based on science, and we have used 4 driving science themes to define what the system should be and do, and to define the operations plan. And these 4 science themes are specific so that we can do that design and planning work, but of course they allow us to encompass a much broader range of total science that will be enabled by the community. So the 4 science themes are probing dark matter and dark energy, where we use a variety of probes to get at those cosmological parameters. An inventory of the solar system, where we're going to take, add millions and millions of new solar system objects, including trans-Newtonian objects and near-Earth asteroids, comets, and other things. We are exploring the transient optical sky. So this is the aspect of repeatedly observing the same point on the sky many times over 10 years to find out what's changing, what's variable, what's a transient, and produce alerts so that we can give those to the community and they can follow them up with other telescope resources. And of course, we're mapping the Milky Way. So we'll produce a map of the Milky Way much deeper in the halo and help understand the ultimate formation and evolution of the Milky Way galaxy. These science themes were selected in the early 2000s, and they've held up very well. They continue to be relevant to help us plan for what we're going to do with Reuben. And in particular, they've been mentioned and further developed in the most two recent decadal surveys produced by the U.S. science community. So in one slide, what we're all about is this legacy survey of time. It's a uniform sky survey of the entire southern sky and a little bit in the north, and a color movie. So we will observe that wide, fast and deep area, the green area in this all sky image or plot. That will cover about 800 or so observations on each point of the sky over 10 years. And those other areas will be mini surveys or so-called deep drilling fields, the little yellow spots are the deep drilling fields where we'll stare over time at a much higher cadence for transient science. So the combination of these will comprise the LSST and will be what we're delivering over the 10-year survey. We'll get down to 27.5 magnitudes in R band over a 10-year period. And we're doing this in a 6 filter set that covers the ultraviolet all the way to the near infrared, about 1 micron. So if you just think of our operations critical partners, it's still a global activity. We have the telescope in Chile. We have headquarters in Tucson, Arizona, and a data facility in California, where actually right now is where the camera is being built. And we have processing centers in France and the UK. And they're all connected by these long haul networks that we're talking about here today. So critically, is the long haul network that gets the data from Chile up to the data facility in California. And then our DOE partners at ESNet are helping us get the data over to Europe for the joint processing activity that will take place there. In the Reuben Net meeting in the next few days, we'll be able to talk more details about how we're doing that joint processing and how all the networks are playing together. It's really coming together quite well. I'm quite pleased with how that's shaking out. This is a slide that Christian produced. Thank you, Christian. It shows the overall long haul network topology with our telescope there on the right, producing the data that gets sent to La Serena and then transferred by the long haul networks up to the US data facility in California at SLAC. Richard Dubois is with us. He's heading up the US data facility for SLAC, and we'll have a chance to talk to him more as the week goes on as well. I don't know, Christian, if you want to add any more specific details to this slide. I can pause for a second.
Yeah, thank you, Bob, and good morning, everybody. Yeah, indeed, this is the big picture of the transfer of data from the summit to the USDF. The main links that we use to do this are, of course, in the long haul network are the 100 gig dedicated link that we have and the 40 gigs backup link that we have. That's a shared connection. The connection from the summit to the base is composed of several fibers dedicated for data and control network, and where you're also installing a new connection between summit and the base, a backup connection. There's going to be wireless. That's in progress as we speak, and should be in production this year. Yeah, thank you, Bob.
Thank you, and we'll have time to ask Christian more questions as we go through the next few days too, for those that have them. So just to give you now a brief status update on where we're at, everything, of course, for operations relies on finishing the construction project, and the construction project is making great progress. But of course, like everyone else in the world, we've had challenges with the pandemic for the last couple of years. The current baseline schedule of the telescope now has us looking at engineering first light with our commissioning camera in the middle of 2023. And with the full camera, which is still in California, but should ship to Chile later this year in late 2023. And then with those dates, we've set as a planning date, the April 1st, 2024 for the start of operations. I think that's probably still a little bit optimistic when everything shakes out. There's still a lot going on with the pandemic and vendors and supply chains and whatnot. So even though the pandemic seems to be getting better for many of us in our operational sites, the follow-on impact of it for the last 2 years is still meaning we're not 100% as efficient as we otherwise might have been. So all these milestones set our observing our operations plan, and we have recently submitted that plan to the agencies, and it's being it has been reviewed, I think, successfully. So we're hopeful that the operations plan and the funding will just now keep working with the agencies to push that ahead as we approach operations. So here's a few pictures, recent pictures of progress. The dome facility is essentially complete there on the mountain. The enclosure is now all enclosed, and we're wrapping up working on the software control of the dome and the facility. There's a telescope inside that works on both axes and has motors, and the control system is being tested, software being tested in the next few months, and hopefully that will all be handed over to the construction team, our Reuben team itself, and the vendors will finish all their work later this summer, and then it will be all within Reuben's hands to finish this up as we go to 2023 and early 2024. On the right there is a picture of the fully integrated camera in California at the facility at SLAC. And so what you're seeing on the right is the camera body. Inside that black round structure is the vacuum vessel with the full focal plane in there that's being integrated and tested right now. It's final testing. We hope never to open that up again, but we'll see. And then as you go from right to left, all that equipment on the back end is what we call the utility trunk. So it's all the feeds that get into the camera and pull the data out and do all the control of the camera. So that's fully integrated, and we expect the testing to continue this year, and hopefully that will ship to Chile by the end of this calendar year about. On the left bottom there, you see some big items in our facility on Cerro Pachon inside that lower facility there below the dome. And those are the M2, the M1 and M3 on the right, and the commissioning camera there, which is a full mock-up of the real camera. And those three things are actually operating now as a system like they would on the telescope. Of course, they're not yet installed on the telescope, but will all be installed later this year as we proceed in commissioning. And so they're being used to develop the software that will control all those key elements of the system as we actually commission the things on Sky. The mirrors, of course, are not in there. They're all ready and they're on the mountain. But what's in there now are dummy mirrors for the testing. And the camera takes images now. It's fully operational. That's the commissioning camera, which is about 1/10 the size of the main camera. This is progress on our network infrastructure. So we're building all the infrastructure for the network and the gear up on Cerro Pachon there. With the computer room there on the left, and you're seeing some fibers there on the right that are lit up and being installed in the telescope assembly itself, and some monitoring equipment. Christian, do you want to give a few more words about this status slide?
Yeah, sure. Thank you. So as Bob mentioned, as we approach to operations, we are preparing our infrastructure. The image from the top left is the summit computer rooms. We have make some isolations to the cold aisles of the computer room. We reduce the temperature of the servers by 30%. We have made a huge improvements to our monitoring tools, and the picture in the middle, that's the fiber that is coming from the computer room to the top of the mount assembly. That's going to connect the camera. That was a huge achievement of this year. It took us several months to make it. It's about 160 meters of fiber going through all the building of Reuben. And some of the things that we have been doing this year is the installation of the Tucson test stand, the TTS. We also dismantled the NCSA test stand, the NTS, and that's soon to become the base testnet, BTS. And we also did our internal network review this year. We're preparing our migration from ACI. We are working also in our backup link, and we have made several cybersecurity improvements to the network. Yeah. Thank you, Bob. Back to you.
Christian. So as we move through pre-operations, get ready for operations, one of the things that we're working hard on are so-called data previews. So these are data sets that we can provide to the community in advance of the full survey. There's 3 of them. The first one is ongoing and will continue this year. In June, we'll release a new data set. These are called DP0, that's simulated data that came from the Dark Energy Science Collaboration. DP1 will be surrounding any data that we get that's science quality from the commissioning camera, and DP2 will be science quality data that comes out of the science validation surveys at the end of commissioning. There's a timeline there at the top. I'll let you look it over at your leisure. There's some significant uncertainty that we try and capture there, and probably this still will continue to change a bit as everything shakes out on the mountain and the finish of the construction project. But the important part I wanted to show you with this table is that we're systematically developing data products and releasing more and more as each of these data previews goes forward toward data release 1, which will now be in 2025. And then data release 2, we'll have data releases follow basically on an annual cadence after that. And by the time we get to DP2, the science validation series, we've almost got all the data products there. It's just adding a little bit more with the solar system catalogs as we move into DR1. I wanted to say just a few words about broader impacts. This is a very important area for Reuben. We feel like with this world best data set that's coming and the ability of us to provide it to basically anywhere in the world, this is a chance for us to include folks in the science enterprise that haven't been able to join fully before because they haven't had telescopes or access or resources to do that. And so it's incumbent on us to provide that data. We will do that, and the tools and the access platform and the training and support to be able to do that. So we're committed to doing that. We've established an inclusion working group where we're reaching out to a lot of folks in historically underserved institutions and bringing them into DP0 already and getting them trained up, those that want to join us, and we'll continue to work with that community as we go forward. We have a dedicated postdoc that will start later this year, will be part of our community engagement team, specifically to work with this aspect of the community and support them and give them the training and the understanding of our tools and data that they'll need to be successful, both in research and perhaps in some cases for educators as well. Our EPO program, I didn't have a chance to talk about it, but it's novel, it's unique, it's really based on Reuben data, and it'll show new ways to connect to educators, students, and the public. Of course, all our software is open source, and we're happy to share it and make that available. The support of it is on a best effort basis, of course. And we are launching on new sustainability initiatives where we hope to make a difference and reduce our carbon footprint as we go forward. So in summary, we're just about ready to launch on this major unprecedented survey, the LSST. It's all down to the last couple of years now. It's going to be a hectic but exciting time. We'll produce this uniform science-ready data set for our community, and we're committed to including everyone in the science enterprise that we can. So thank you very much. I think I maybe was just a hair over time. Sorry about that, Julio.
It's okay, Bob. I think we'll catch up as we go through the morning. Any questions for Bob and Christian?
We do have a question in the chat.
Yeah, nothing in the chat.
No, there is something in the chat. It's
Okay,
from
there is.
Adele.
Yes. Okay, Adele, you want to ask your question?
Sure, thanks for the presentation and exciting progress there, Bob. I was wondering, maybe I missed it, but how big are the data products from DP0, DP1, and finally DR1 and 2? And how do you plan to deliver those to the community?
Yeah, so all the data are now being made available through our science platform. We call it the Reuben Science Platform. It's a Python-based, web-based notebooks with an API and a portal to explore the sky and look for images in certain areas. So all the data will go through that science platform. It's currently, we have it deployed on Google Cloud Platform, and that's our plan to do so in the future, but it may be at Slack as well. We haven't quite decided that in conjunction with Department of Energy. But in any case, the data releases will be growing from, we're taking about 5 petabytes of image data per year. And the total archive holdings will grow to about half an exabyte with all the intermediate data products by the end of the 10-year survey. So each data release, the catalogs will be somewhat smaller than that are available through the science platform. And the whole data holdings will be available as needed. But we envision mostly a smaller amount of data in the cloud that people will use over time. Richard's on. I don't know if Richard can add a little bit more detail to my vague answer.
Sure. So yeah, so the main access will be, we think, through the object catalog, and I think by year 10, that's like 15 petabytes. That's getting to be a good size beast. And we built a custom astronomical query database for that. So yeah, so we will have our science users in the cloud, and they'll be talking to that server at Slack. And we're still trying to figure out what images they're going to want. And so as we go through the data preview process, hopefully we'll get some experience there.
I think we have a plot that shows how our data volume of different types grows over time. Adele, we can send that to you.
That'd be really nice. Thank you.
And I'll show it tomorrow.
Okay. Any other questions for Bob?
It's like Eli has his hand up.
Hey, morning. Thanks, Bob. So on this same thread of data access and so forth, something that we're starting to see in some other science communities is people sort of doing things with the data that weren't anticipated previously, right? Like the machine learning people wanted to sort of grab a whole bunch of stuff and jam it through whatever their model is to try and explore stuff. By the time we get 10 years out from today, 15 petabytes is going to feel a lot smaller than it feels now. I'm just sort of curious what the future plans are there.
Well, I think we'll probably have to be community driven and see what people actually want to do. We know that we already have certain key stakeholders like the Dark Energy Science Collaboration that will require us to move a goodly amount of data to other computing sites. And we're hoping that hope is not quite the right word. We're excited about the cloud in that at least we know that we can expand there to address the need for more computing cycles without having to continually necessarily, build up our own hardware continually at Slack. But we're concerned about the price, and we don't know exactly how that's going to grow over time. So I guess we're taking an approach where we'll, we want to use these data previews to try and understand the user patterns better and the user needs and what they really want to do. And I think by the time we get to data preview 2, which is really a good chunk of data from the LSST cam itself, we'll start to understand that better. And then we're just going to have to, adapt as we can going forward. Our plan has been for a long time that we would provide 10% of our overall computing budget. So we know what it takes to crunch the entire survey and produce the data products we want to produce. But we really, like you say, things are evolving. We don't know exactly what the users are going to want to do. So we've always said we would set aside 10%. I think we probably all think now that's probably not going to be enough. And so we're thinking of new ways to allow for greater computing resources to be brought. This could be more at other DOE labs, could be more in the cloud, could be that we have data in the cloud and we allow users to bring their own resources, their own credits to do things. So we'll just have to see as we go forward how this shakes out.
Yeah. Okay. I mean, the thing that I'm sort of contrasting in my head, right, is computing that the project provides for itself, right, for what the community wants, and then there's allocation-based computing at national facilities.
Mm-hmm.
You know, whether that's, you know, TAC or NERSC or whoever, right? And you know, the cloud version's easy if you've already got the data there. Just like, you know, a computing facilities version is easy if you've already got the data there, right? The fun part comes when it's not co-located and you need to pull them together. So anyway, I will be watching that with interest also. So thank you.
Great, thanks.
Thanks, Eli. Let's move on to the next talk. And if any other questions for Bob and Christian and Richard, just put them in the chat or hold them till we have the open discussions later later in the day. Okay, so our next presentation is NORLab. Is it who's speaking on NORLab? Is it Chris or Mauricio? I have Chris, Mauricio, and Eduardo in the agenda.
Yes, it's going to be all three of us.
Okay, great. So go ahead.
Okay, thanks, Julio. Yeah, thanks, Bob, Christian. Very interesting. Okay, so I will only be speaking for a short while, then handing over to Mauricio Rojas and Eduardo Toro to talk about the details and things that are going on in NORLab. So my name is Chris Morrison. I'm the head of IT operations for NORLab, overseeing the integration of the programs into what is now currently NORLab. So next slide, please. So we're going to talk today just briefly about a general overview of NORLab, just a refresher of what NORLab is, and a quick explanation of IT operations and what we do and what we look after. Then Mauricio and Eduardo are going to talk about the backbone activity and network activity. So there was a little line you saw there in Bob and Christian's presentation, the aura part of that pipe, and that's the part that we're looking after. Talking about the program integration, so how the programs are being or becoming part of NORLab and what our role in that activity is, and then the general network upgrade project and what's happening there. So next slide, please. So yeah, for NORLab, this is straight from NORLab's webpage. The mission of NORLab is to enable breakthrough discoveries in astrophysics, developing and operating state-of-the-art ground-based observatories and providing data products and services for a diverse, inclusive community. So straight from the website. For us, the important thing is NORLab is 5 programs. So Cerro Tololo Inter-American Observatory, CTIO, Kitt Peak, CSDC, so the Community Science and Data Center, the Gemini Observatory, and then when then moves into operations, also the Verity Reuben Observatory as well. For us, also in NORLab, we provide several services to what we call tenants, services such as summit-based connectivity, so providing the bandwidth for several tenants that are on Cerro Tololo, for example, or on Kitt Peak, and also access to the research and commodity internets and all of this through special agreements. So these are the programs here that we mentioned, the 5 programs that operated, Aura operates these under a cooperative agreement with the NSF. Next slide, please. So for IT ops, IT operations, we generally look after IT, everything that's IT within these programs, or as we start to move forward, more and more we're getting involved. And of course, our underlying plan is to standardize the development or the deployment and management of all the IT infrastructure and all the support for IT as well at all levels throughout NOIR Lab. So for us, this includes astronomy IT operations and business IT operations and everything else that's in between. So just roughly, what we consider IT or astronomy IT operations is everything that's required to support science and delivery of data to the science community. Business IT operations is everything else that's required to run the organizations and run the programs. So this is anything you can generally understand as typical email systems, end user support, cybersecurity, and enterprise infrastructure. So a relatively small team, but they're distributed across all the sites between Chile, Hawaii, and Tucson. There's 24 of us providing the support for both business and IT and astronomy IT. There are some programs where we already offer a lot of astronomy IT, so all the way into the dome. For example, in Gemini, IT operations is directly involved all the way up to telescope controls, where it's then handed over to the software team. So next slide, please. So with that, I'll hand over to Mauricio, who's going to talk about these next items, the backbone network activities. So Mauricio, all yours.
Good morning, everybody. Next slide, please. Hi. The NOIR Lab's international links between Chile and USA, it's provided by AMPATH. AMPATH provides 2 links from Chile to Miami at 10 gigabits per second, versatile to 40 gigabits per second. The primary link is seated on the Pacific coast, and the backup link is seated on the Atlantic coast. In case of problem with these links, Reuben kindly provide us a backup link of 10 gigabits per second on a shared link. Thank you, Reuben, guys. Next slide, please. The NOIR Lab's national link between La Serena and Santiago is provided by Reuben. Reuben provides us a 40 gigabits per second link on a primary link through the internal valleys, the red line, and a backup link of 4 gigabits per second along the coast using the route number 5. Next slide, please. The communication between La Serena and Cerro Pachón is provided by NOIR Lab. NOIR Lab provides a 20 per 10 gigabits per second link on a fiber using the DWDM equipment. And NOIR Lab provides several backup links to sustain the operations and data transfer in case of problem with the primary link. We have a link between La Serena and Cerro Tololo, 400 megabits per second. A link between Cerro Tololo and Cerro Pachón of 300 megabits per second. We have 300 megabits per second from La Serena to Cerro Tololo, and a 200 megabits per second link between Cerro Tololo and Cerro Pachón. Additionally, NOIR Labs provide a 300 megabits per second between La Serena and Cerro Pachón to communicate Gemini and the base data center. Next slide, please. This slide shows the initial deployment of the DWDM from La Serena to Cerro Pachón. This configuration doesn't include the backup link between the programs. This configuration includes a pair of fiber for each program to join the BDC, the base data center, to the data center at the mountains, Caseta de Comunicaciones in case of NOIR Lab, and Reuben data center at the Cerro Pachón. Next slide, please. At the moment, Reuben is deploying a solution to finally close the DWDM ring between La Serena and Cerro Pachón. It means that in case of problem with the singular fiber of a program, all the traffic will be moved through the other DWDM equipment, going down to La Serena and reach the other DWDM equipment to reach the network needed. It's a very, very useful thing. Next slide, please. This slide is related to the Carnegie. In the past, Carnegie the only path that Carnegie used was this yellow line between the computer room in Colina El Pino, La Serena, to the base data center. All the traffic from the mountain and El Pino was transferred through this fiber. Over the past weeks, Noir Lab IT groups and LCO IT group have been working to improve this connectivity. Cerro Las Campanas, Colina El Pino, and base data center are connected to the same switch at the internet service provider. This is the Riuna switch. At the moment, all the traffic going from Las Campanas to the internet is passing through this switch, going to the base data center to finally reach the internet connection. If the traffic from Las Campanas is going to Colina El Pino, it's going to this common switch to reach the Colina El Pino in La Serena. In case of La Serena office, if the traffic goes to Cerro Las Campanas, it goes through the route to the common switch and finally reach Cerro Las Campanas. It is a known link between LCO and the internet service provider. In case of Colina El Pino is trying to reach internet, it's using currently this 23 years old fiber. The next step is move all the traffic from Colina El Pino to the red line new fiber to reach this common switch to get the communication to the base data center to finally reach the internet. That's the very good improvement, because in case of problem with the data center of Colina El Pino, the mountain will be connected to the internet through our infrastructure. The same thing happens if the problem is found here on Las Campanas, the mountain. Next slide, please. To continue the conversation, Eduardo will talk about the Gemini and MSO integration, the improvements during the last year, and Noir Lab Network Upgrade. It's a very interesting project. Thank you. Eduardo.
Okay. Thank you, Mauricio. Hello, everybody. We will start this last part of this presentation is related basically of these three items. We will talk about Gemini and medium scale observatory integration, data ops improvements. Part of them was mentioned by, in this case, Mauricio, and also we will talk a bit about the Noir Lab Network Upgrade project. During the 2021 activities, we are still focused on a lot of strategic activities in order to integrate the programs of Noir Lab in the South. We have Gemini, we have CTIO, we have others. We are working in a key element of the Noir Lab upgrade, which is the network upgrade project. We are working on it, working in the definitions about the new architecture of this new project, in the wired and the Wi-Fi activities, where we are defining the new elements that we need to consider. We will talk about in the next slide. Additionally to that, we complete an important upgrade in the infrastructure related with the network upgrade. We will change the traffic of CTIO, but also we are put some emphasis in terms of the SSL VPN remote access. And the last but not the least, we are still working in the work activities. We have some projects in progress, maybe in a standby, to be honest. But that create a much better environment in order to work with inside of the Noir Lab. This is the diagram, general overview about the activities of the integrations of Gemini South and CTIO in La Serena. In the left hand, you have the Gemini data centers with all the present architecture. And the right hand, you have the architecture simplify of the CTIO in La Serena. We have the base data centers. We are sharing the same space with Vera Reuben Observatory. So in this case, you can see the current scenario where we complete the final firewall upgrades. And also we still modifying all this infrastructure in a new model that we are in this process thinking in the network upgrade project. Additionally to that, it's important to understand we have many network services in terms of the cybersecurity based on the new generation firewalls, and also we have many inside network services that provide the authentication, authorizations, and many activities that we need to the functionality of the network. More in details, the next generation firewalls, basically, we increase the number of tunnel profiles. We created a new architecture in order to provide remote access to contractors, to visitors, etc. We have an initiative with SOC, which is an institution sponsored by the National Science Foundation in order to determine the risk and the threats from the cybersecurity point of view. We also work in the CTO traffic control that I mentioned before is now moved to the next generation firewalls. And also we are working in the implementation of the current functionality of the ITOps in that devices. An important activity about the backbone devices is the software upgrade that we are doing, still in progress in the Nexus devices with NX OS operating system. And also we complete network services and collaborative tools of Knowledge Labs in order to provide the functionality in the next years, basically based in the authentication authorizations, the centralized service desk, and also we complete also the unified productivity suite that we deploy to all Knowledge Lab staff. And in particular, we are absolutely interested into promote and the collaboration and integration with Reuben, since they are right now in constructions, but we still have some activities in order to coordinate properly our IT activities. What about the Knowledge Lab Network Upgrade project? Well, it's an important project in order to design the local area network in all the locations. We are in the phase of the design. The locations, to everybody knows, is La Serena, Cerro Pachón, Cerro Dololo in Chile, and we have Hilo, Mauna Kea in Hawaii, and Tucson and Tepic in Arizona. We also consider an upgrade of the Wi-Fi and also a review of the wide area network design. And what part of the design we're basically talking about the standard technologies that we have some options in the market, still valid for us considering our size, our needs and requirements. It's still working the traditional multi-tier design. We're still evaluating some vendors or traditional vendors that we have in our infrastructure. We are analyzing the core distribution access topologies or any technology like based in stacking. At the same time, we are looking for a new fabric layer 2 leaf spine that we permit to be in the state of the art of the data center technology. Some of the activities or some of the options that we have possible. So we are studying some vendor capabilities. We mentioned some of them in the list. We are expecting to finish this in 3 years to cover all locations. And also this involves obviously important Knowledge Lab stakeholders. And this last, one of the options that we have possible is a traditional multi-tier design that you can see here. This is basically that we are trying to do is just to increase the uplinks between the different data centers, change completely the core, obviously the distribution and the access devices. We are considering just a small segment of the Knowledge Lab in Chile, but following our experience, that probably we will reply this in another part of the Knowledge Lab and in other locations. You can see here in the left side, the Yamane data center, and the right, the base data center, where we include the core to the whole network, but also we will improve the medium scale observatories network that needs to be updated. So this is one of the options that we have possible. And we have another topology 2 that is based in a leaf, layer 2 leaf and spine, based in spine and leaf devices. Some of them places in the base data center and also in Gemini data centers. And we are concentrated all this new architecture in the next months or years that will depend on the
Did we lose audio with Eduardo? I don't hear him.
Yeah, yes.
I think so.
I was afraid it was just me.
Everyone in Chile.
Everyone in Chile?
I don't.
I'm still on.
Oh,
Okay, there's Albert. That's good.
Lost Lena.
Okay.
Yeah, it looks like Chris is gone and Eduardo. Oh, Christian's still on.
Charlie's there, I think.
Yes, Alma is still here.
Great.
Okay.
Yeah, there he is.
Now you're back.
Eduardo? Okay. Please continue.
Yes, well, just to finish, this is the last slide. It's related with the second option that we have. And if you have any questions, please.
Okay, we have time for, I think, one question for the NOR Lab team. Any questions? Vasi, do you have a question?
Yes, so I have a question about the data volume transfer over the network and if where are the locations of the data archive?
I can mention that we are under the gathering requirements from different programs inside of NOR Lab. We don't have a clear number right now because the programs after that integrate inside of NOR Lab have different options in terms of the archives. Gemini, for example, is still using Amazon Web Services, and we have another with the CSDC, for example, which is another program. So we are gathering that documents, but in terms of the data archive, we have in Tucson, we have some other archives in La Serena, Chile, another in Hilo. But Gemini as programs, it has Amazon Web Service for that. It's still gated in that activity.
Okay, thank you. Thank you very much. I think Christian has a comment or question.
Yes, I have a question for Mauricio. Mauricio, I noticed you had 2 backup links from Summit to Base. Will you mind expanding on that?
Sorry, I had a little problem with the internet connection. You mentioned we have 2 backup links from the mountain to La Serena, right?
Yeah.
Yeah, not by the moment. We are trying to improve the connectivity before think about that.
Okay, so all right, so this is a plan for the future, I guess.
Yes.
All right, thank you.
Okay, let's then move on to NRAO and NGVLA. David and Adele, you ready?
I believe so. Can everyone see that?
Yes.
Okay, excellent. We're already winning. We should quit while the network's still working. But wait, there's more. Okay, so Adele is there to support questions and science. I am merely here as the messenger for all the good work of many hundreds of employees. And we're a little bit the wrong way around in that the ALMA-centric Chilean network will be presented next, but I'll mention that as we go forwards. First of all, just to get the important stuff out of the way, the National Radio Astronomy Observatory is a facility of the National Science Foundation, operated under a cooperative agreement with the Associated Universities Incorporated up in DC. Okay, there's a pretty picture of ALMA at night, very beautiful. So NREO and ALMA, we are one of the 3 regional centers. The other 2 are, of course, over in Europe, in Germany, and East Asia in Japan. But I'll focus on the North American ALMA Science Center. Forgive me if I call it the NASC. So the ALMA telescope, brief introduction. I won't read all the way through it, but it has 50 12-meter antennas. If you think of 12 meters, it's larger than the room you're probably in. These are very large single instruments, and then combined together, we will come to in a primer for how we do that magic. And then there's a subcompact array, the 7-meter 12 dishes. It is kind of operated in a PI mode as the focus. For the observations, the cycles, we're moving into cycle 9 calls. The end of that, as Adele can attest, is in a couple of days' time, or I think 47 hours if you want to get particular. So it's a great push once a year to get your time on the sky, and this is a very heavily oversubscribed instrument. And then the data flows out to the regions, as we'll come to in a minute. But first, an introduction to radio astronomy. I wanted to shoehorn this in, and apologies if it's a bit of a sidetrack, but how on earth do you get all these instruments to perform together as a single telescope? And we'll use the Very Large Array as an example in the plains of the St. Augustine Desert in New Mexico. So these are 27 dishes, and if they all point at a single object in the sky, you can do some magic with high performance computing. And this is called Aperture Synthesis. So you turn all these individual dishes into a single telescope. So this is the math behind it. 2 dishes pointing at the same object in the sky will cause an interference fringe for the point where they overlap, and will cancel out all the noise where they don't overlap. And this is the huge advantage of an interferometer as opposed to a single dish. You can cancel out all the noise that aren't in the focal plane. Or as a comic put, if you have 2 small dogs, you can simulate a very large dog. And it really is that fascinating to see how computing can help this work. Quite simply, you have that interference fringe, like you will remember from high school, the Young's double slit experiment. Each dish is 1 slit, and then the pair of dishes produce 1 fringe. Every single pair of dishes produces their own fringe, so this scales with the number of dishes squared. So, you know, tens of dishes gives you hundreds of baselines. Hundreds of dishes gives you tens of thousands of baselines. So n squared is a very powerful number when you come to scaling. And then you stack these together over time. And I don't know if this animation will work, but it basically shows these interference fringes adding together to give you an image on the sky. And it's also important to note that these telescopes look at the object, the same point in the sky, for minutes or even hours. And as the Earth rotates, it fills in this image plane. This is the correlator. This is actually 1 quadrant of the correlator. This is 1990s technology, built in the 2000s and went operational in about 2010. First light on ALMA was that far back. Cycle 0 was in 2011, and we've been running through cycles ever since. I won't go into details on that, but it is a very high performance, high throughput computer, and it works in peta operations. Of course, it doesn't do floating point operations per second. These are just several bits, add, multiply, very, very fast. This is the schematic for ALMA. As you'll see, the correlator sits at the heart of all of the dishes. And we will just be concerned with this bit. After the correlator's data flows from 16,000 feet down to the operation support facilities, about 7,000 feet, and then off to Santiago Central Office, where JAO resides, and then out to the 3 regional centers. Okay, transport in Chile, I won't go over this, but it gets from the high site down to Santiago in short order. That will be the next presentation. And then it goes from Santiago to the regional centers. We share a link with Aura for 10 gigabits of capacity, of which 1 gigabit is committed. And as I say, after the correlator, the data rates are not so scary. So 600 megabits per second is a goodly amount of data transfer sustained for us now. And we could do with a little bit more, as we'll come to in a second. So how does the archive grow over the last several years? It's been growing at, I don't know, 19 terabytes per month, hundreds of terabytes per year, increased in cycle 8. And of course, this is driven by the capabilities of the instrument, but also by the projects that are proposed for the telescope. So PI driven means it's a little bit unpredictable, but then of course, after 1 year, all of this data is made available to everyone. We have an open skies policy. And of course, archive research takes a little bit of time when you try to reuse other observations, but that is definitely increasing. As you will see, there's been a plateau because ALMA had to shut down because of its very nature. We couldn't transport people to operate the telescope during the pandemic, but it's come roaring back with cycle 8 moving into cycle 9. This is how the data archive is projected to grow over the next few cycles, and as I say, 0.5 petabyte a year. This is committed in perpetuity. We host this at 4 locations. And so, you know, when will ALMA stop observing? It will get a major forklift upgrade in the 2030s, but the VLA was commissioned in the 80s, and 40 years later, it's still going strong. And we'll come back to that in a minute also. Opportunities. So everyone's seen this image, everyone on Earth, which is kind of scary. So back in 2017, observations were taken of the M87 black hole. And then in 2019, it was made public to the world. And as you can see from the top top right, there were many instruments involved in this, including ALMA. And because of the nature of these sites, disk packs were shipped. Physical data was moved around the Earth via carriers. FedEx was our friend. And so this is very hard to imagine in modern day, but if you look at the bandwidth of a freight train, it is quite remarkable. However, is this the future? We hope not. Certainly, as the ViraC Reuben comes online, the target of opportunity, the ability to not only rapidly observe, but also process and analyze and then iterate on that information. Multi-messenger is the future. Real-time observing is the future. So as we look at other opportunities, I won't go into details, but Adele has all the gory information on this. There are many opportunities for other kinds of science that can be done if we had more bandwidth, more capabilities. So this is definitely the future, and we look forward to increasing the data rates sustained and also real-time burstable in these areas. Adele, any comments on this for the wider community?
I guess we wanted to mention that these are not the primary scientific questions, not being used, 99% of the time, but they would be some of the very impactful science. And so it's really important that we enable this for the larger community.
Yeah, that's a really good point. As we increase capabilities, we enable new science. If the capabilities aren't there because we don't have the bandwidth, we get into this negative cycle of doing what you did. And we really want to maximize the impact of this telescope. Also, the correlator that was built in Charlottesville in the 90s and designed in the 90s, built in the 2000s, needs to be upgraded. We'll be partnering to do this. And this will be moving towards ALMA 2030. So the midlife upgrade, or not even midlife, teenage upgrade will involve upgrading the correlator for much greater capabilities. And then that will inherently increase the data rates by many factors to probably a petabyte a year sustained, but of course, long baselines, you can get instantaneous bursts of very high bandwidth requests. This is one of the ones that keeps me awake. We have had failures. In fact, we had an archive issue just this week before proposal deadline, which slowed down the data rates of access. So we had to point our hungry customers at Europe for a little while until we figured that out, which was fine. You know, it's real time, and Europe was very able to handle the load, which is much appreciated, but that cannot be the plan if we lost all data through a catastrophic event at one of the regional centers. We would look at the primary archive in Chile for this. So 1 gigabit link sustained, it would take 5 to 6 months to restore the data, which is just not acceptable. So would we be shipping large crates of disks? We hope not, but this is an example where extraordinary situations would require extraordinary activity. And my disaster recovery plan is usually 2 weeks of downtime is where you get intolerable for the community. So we've got an order of magnitude problem there. Future cycles, I won't go into too much detail because it's reiterating what I've already said. But the push is, of course, for science-ready data products, interactive portals, where users can do new and innovative science, not by looking at any given data set, but by surging laterally across multiple observations, not just from ALMA, but from all the NRO instruments and all telescopes in general. Astronomy cannot be limited to a single frequency. And then summary, again, we just need the access to more bandwidth in a coordinated fashion. But factors of 4 over the next few years, we should be able to manage that. You know, Aura has been a good partner so far. It's not clear how that proceeds in the long term, but certainly we look forward to continuing to rely on this community to service the unique telescope that is ALMA. Quick pause for questions before we go on to the more challenging next generation VLA. And please feel free to drop them in the comments. Adele, if you can have a look at those and interrupt. Question?
Yeah, I think there is a question from John Graham.
Please go ahead.
I can just speak it. I was wondering, how do we address the last 10-mile issue to get bandwidth to observatories? Apache Point Observatory is 10 miles from 200 gig capable networks.
Yes. Yeah, and as I say, this is the key challenge that we are embracing, the idea that you shouldn't be downloading your data. That's very strange. That should become, you know, like the old days when you had to download a movie to watch it. You should be watching it on demand with remote infrastructure, and the bandwidth is just what you need to light up your screen.
Yeah, they barely have DSL currently there, but
yes. No, good point. We actually have a collaboration with SpaceX and the Apache Nation, out in New Mexico, Navajo native tribes are test participants in this. And they have, I think, 15 of these SpaceX points. We are using the VLA to go look at the horizon and see how much that radio frequency interference would challenge us. We're seeing very good results at the moment that if you don't have line of sight to the telescope, you can get many tens of megabits per user for these community-based installations. So we're definitely very aware of not only RFI, but the fact that it's a reality from the number of constellation satellites. And the FCC is relying on National Science Foundation to do spectrum management. So we're really hopeful that we can have a win-win of a managed spectrum on, you know, terrestrial that can provide usable bandwidth. If you can stream a movie, you should be able to interact with science data. So that is in our vision of enabling access cloud-based remote infrastructure hosted wherever. At the moment, NREO has a fairly significant investment in this, but we're looking at, of course, partnering with the grid providers and the cloud providers to have capacity on demand. Yes, it's
Albert, you have a question?
Go ahead.
Yes, I'm sorry, I missed the time frame of the 10G link that you mentioned in your previous slide, and I'm wondering if you mentioned that if there is the need for a recovery plan disaster, probably we could think in a more bandwidth than that. At least from the Reuben's point of view, we have a 100G capacity to print. So probably if it's something that is needed, we are technically capable of doing it.
Yeah, I hear you entirely, and Julio and I have a date for a call to negotiate and coordinate that, not just baseline, but also incremental need-based, time-based reservations, capacity on demand. This is all the research where we partner to enable research on using the network. So yeah, I hear you 100%. 1 gigabit is not what it used to be. Certainly, we would like to remove any constraint over international bandwidth for ALMA.
Okay, great.
Okay, let's
Great.
move on in the interest
Carry
of
on, David.
time. Yeah, please. Forgive me if I give everyone seasickness. Can everyone see that one? NGBLA?
Yes, yes.
Excellent. Okay, so this is a lot more wet paint, but that's why we're talking about it. Next generation, very large array. As I say, 40th birthday, midlife crisis, structural integrity. Arecibo is about the same age, and while that was a massive single dish, it's not the same, but it is similar. The iron that we observe with has not changed in 40 years. The optics, the receivers, the correlator, they've all changed, but the fact that we still have 40-year-old trains picking up these dishes every 4 months, this, we need to move forward with the very large array, and we're proposing the next generation very large array because we love the name. This was very highly rated in Astro 2020 decadal survey, which I'm sure everyone here has read and attended with riveted interest. It is the way we tee things up for 2030. We don't want to wait in line for another 10 years, that's for sure. I won't go into too much detail, but we were on the highly recommended that you should just do it horizon for enabling astronomy. And of course, ground-based astronomy is just so orders of magnitude cheaper than space-based. It's in the long-range plan for Canada, and we're partnering with the Americas and even the world on this. This is a multi-billion-dollar telescope, and we want to make sure that it's accessible and diversely funded and accessible. So what will it look like? Well, it'll look like a lot of 18-meter dishes. And the reason Rob Salina couldn't be here as he was last year is because we are working up to a preliminary design review for the dishes. You want to get the first one built properly, and we are in the process of defining that. And then we'll have 260 more of those dishes for go live in 2030 something. This is the frequency range. I won't go into too much detail, but we have multiple duos down to liquid helium temperatures in the middle of a desert. So this will have power requirements, cooling requirements, communication requirements. We'll focus on communication requirements in this presentation. There's a main array, a short baseline array, and then a long baseline array. And we'll be focusing on the long baseline array because that needs fiber optic you don't own. Frequency coverage is 1 to 116 gigahertz, so it is a spectacular range of frequencies. So I'm not sure which way round you want to go. Let's go from bottom left. This is the middle, and then we work out to upper left where we can see the states. It's focused in New Mexico, just to the southwest of the current VLA site, and these will co-locate and probably cooperate for a few years, but clearly the transition is to not only improve and replace the VLA, but also integrate in the functionality of the very long baseline array. And the very long baseline array is 10 dishes going from Hawaii, 8 on the continental US, and then out to St. Croix in the Virgin Islands. And as you can see, some of the remote locations have multiple of these 18-meter dishes. So 3 dishes at these remote sites. And that will give you the sensitivity as well as the long baseline. So this is where it gets really scary. 244 18-meter elements going up to 20 gigahertz, 8-bit dual polarized, comes out, simple math, to, let's call it, over 700 gigabits per second. And I was going to show the 1.21 gigawatts video from Back to the Future, but I fear copyright. So it's a lot of bandwidth, and this information is just white noise, like you would see on your old TV, until it hits the correlator. So there's no compression. This is all just raw noise from the sky until you cross those beams in the correlator. Won't go into detail on that, but we have the main array, which is a 5-arm spiral, and then that extends out. We predict that data processing, won't go into too much detail, but after it hits the correlator and pops out the other side, it's all imaginable. Again, we do need capacity on demand for this. This will be a PI-driven telescope, so it's hard to predict, but we will also have the ability to do subarrays, so you can do multiple observations concurrently. Serving data to the users, the focus is on science-ready data products, so making the instrument much more accessible. You know, I want to do this science on the sky rather than I want this spectral bandwidth. And the idea that the PI can manipulate the data at the place for the data, where it's stored close to the archive, then simplifies this entire data distribution problem to one of interacting with remote data with capacity on demand. Project timelines, it is the future and always will be to some degree. You never finish building a ground-based interferometer just because of its very nature, but we have several milestones that we have hit. The prototype is the next major milestone, which will be in the next year or two out at the VLA site, where we will learn a lot more about the functionality and control systems, you know, the tolerance to wind, for example, the radio interference, the power requirements. So it is learn by doing to some degree, but we bootstrap into this. And then the NGVLA early science towards the end of the decade, and then full operations in the mid next century. So, you know, for example, ALMA was thought about as the submillimeter array in the 80s. Proposals were ingested in the 1990s, construction in the 2000s, and here we are 10 years next year into operations. So these are decade upon decade. People spend their entire career building and then bringing to life, and then the next career supporting these unique telescopes. James Webb Space Telescope was no easier. So, forgive me, I should have changed the name, but the significant amount of fiber optics, there are so many areas where we will not be able to do this ourselves. And as I say, this spreads out not only through America, US, but North America writ large, the islands, and it is an international investment then to get the data to where it needs to be. So what will the operating model be? We suspect it'll be something along the lines of ALMA, where you have regional centers that enable access for the folks who need to manipulate the data. Okay, sorry for the whirlwind, but that's the next generation VLA as we know it today. Questions?
Very nice, David. Thank you.
I just pasted a link in chat that describes the Shikate. It's Lev Gonik's project out of Arizona State. He's organizing cyber infrastructure for connectivity and planning to spend all the infrastructure dollars that have been invested in the Southwest region. They have an upcoming meeting in June. If somebody's interested in attending that, I can, you can contact Lev, or I can get you in contact.
Yes, I believe we have been in touch with that. Rob, as I say, is feet on the street and he's in Germany. But yes, please send that to me. We can always use building the community, especially in an EPSCoR state like New Mexico. These are just huge drivers, not science drivers, drivers for technology, employment, infrastructure. A similar thing in New Mexico, in West Virginia. You know, Chile is a prime example. They just got the memo, you know, as a country, to understand this is important, not for learning the things you don't know about, but for all the spin-offs. For example, you know, we have about 600 employees, 80 of those are card-carrying radio astronomers. So, you know, generous, call it 15%. Everyone else is kind of pushing along the technology to enable science for a community of many thousands. So yes, as we have the questions, well, how can underserved, underrepresented groups get access to this data and do it in a way that doesn't need you to become a PhD data scientist as well as an astronomer? You know, I just want to do science on the sky. How do we make that accessible? So it does take this community.
Eli, you have a question?
Yeah, I just wanted to, so first, David, thank you for 2 really great talks. And I guess I just wanted to say that if a conversation with ESNet would be helpful to you, we would be delighted to have that conversation. I mean, we have stuff in New Mexico, right? I have no idea whether there's synergy with, you know, what you would need to do in that part of the country too, but be happy to explore that.
Let me assure you, Los Alamos is kind to us. They give us 10 gigabits per second for the existing VLBA location, somewhere out in the woods. And that is just, you know, part of the community that we just appreciate so much. So DOE is there for us. And I think as we look at examples, one thing I didn't mention was, well, I touched on was radio spectrum management, and the idea that as we have 5G, as we have SpaceX, as we have airplanes flying overhead, as we have 5G interfering with the airplanes as they try to land, monitoring the spectrum. How do we know right here next to O'Hare Airport what noise is there right now? And so we are engaged in this research. It's not science research, it's, you know, research on just how much noise is out there and how do we manage these transfer of bandwidth from, you know, what was, you know, C-band, these various analog band allocations now to a much higher, or much narrower bandwidth, where any pollution of sidebands would be devastating for so many people, not just, you know, people watching kitten videos in the desert, but people trying to do their jobs. So one of the examples would be distributed time synchronization. You know, DOE does time synchronization for many reasons. And this is one of our challenges. We can't afford, you know, a $1 million maser at 200 sites. But we can't afford any fiber optics other than pole-based. And as it warms up in the desert, the fiber optic slags only by a few millimeters. But if you're a light particle, that's a lot of femtoseconds. So yeah, we feel the need.
Yeah, okay. Well, to be continued. Thank you.
No doubt. Okay.
Great,
Question?
great. All right, I think we can move on then to the next presentation by Alma, Christian, or Nicolas.
We're here. I am with Nicolas here in Alma.
Okay, floor is yours.
Okay. Can you see the presentation?
Yes.
Okay, let's go. Next slide, please. Okay, thank you very much to David because it was a great talk about ALMA. So we will focus more in what are we doing internally in our links, okay, and what are our next steps, okay. Next slide, please. As David showed, we have a fiber optic link that connect the AUS, the place where the antennas are located at 5,000 meters, with the closest big city, which is Calama, and from there to Antofagasta, and from Antofagasta, we go through the road links to Santiago. So that is working since several years, okay? But we need to do some upgrades in the infrastructure that support that links, and that we are working in during this year and probably the next year. Next slide, please. Here at the right, you can see the three sites that ALMA has in Santiago and OSF and AUS. From Santiago to the US, we have two links of 2 gigabit, the 1 gigabit each one. And from Santiago to the OSF, we have a backup link. It's microwave links with another provider, a different provider, a different ISP. And from the OSF to the US, we have dark fiber. We can put in that line as much data we want. In this moment, I think we have 10 or 20 gigabit, but we can put as many fibers as we can. And from Santiago to the ARCs, there is two different solutions. One solution goes through Rauna that send the information to North America and East Asia. And for ISO, as we are sharing the same campus here in Santiago, we have a direct fiber that connect with them. And from internet, of course, we have our own access to internet. Now, what are we working now? Several equipment in our connection from the AOS to Santiago are obsolete in this moment, and we are working to replace them. Mainly the PATTEC that are connected in the north, we are working to replace, and also not to replace, but also to change the topology a little bit, okay? And ISO is doing the same in their site. They're replacing the Sienna equipment that they have. So at the end of this first step, we hope to release a few gigabit more, a couple of links. Probably ALMA will receive an additional link. So in that case, we'll have three links of 1 giga each. Just for the fact that we will replace obsolete equipment for new one. But in parallel with this, we are working to do an upgrade in those links so we can move from 1 gigabit to at least to 10 gigabit connection between the observatory and Santiago. Next slide, please. The idea is to continue working with DWDM equipment, also replacing the equipment and creating negotiating a new contract with our providers. Okay, next slide, please. Here you can see that the 2 gigabit link that we have connected from the AOS to to the PadTech, and from there, that PadTech we expect to replace, and so we can have at the end 10 gigabit links connecting directly to Santiago. And also, the idea is in the US to install a point of presence of Reuna. So the other observatories that are in the Charnator Plateau working at 5,000 meters have access to those links via Reuna. In that case, they will use the same fiber optic that is installed from the US to Calama, Antofagasta. But in the case of their data, the data will be delivered to Reuna network in Antofagasta. We're talking about cities that are in the coast of the country. For the people that is in the observatories is in the mountain, and these cities are in the coast of the country. So it's anyway, it's a long distance. Next slide, please. And the idea is that the observatories that are being installed in this moment in the Charnator Plateau can access to the fiber optic. We have some fiber optic in the plateau that is not devoted to any path, that is built in the desert itself. So the idea is that we can share part of those a few fibers that to provide access for different observatories, so they can access the Reuna POP in the US. Next slide. And since a few months before the pandemic, we started a laboratory here in Santiago to install a second control room. That was very timely because during the pandemic, when we opened the observatory, we started using the laboratory to operate the observatory remotely. And since then, we continued. Now, most of the observation are controlled from Santiago, from our remote control room, okay? And that is very good because probably in the future, we will need to move our control room, the OSF, to a different position. So we will continue controlling the observation from here in Santiago. We alternate mostly during the day, we control the observation in Santiago, and during the night in the observatory. Next slide. And finally, David already mentioned the ALMA 2030 or 2030 or WSU project, okay, that we're evaluating several things. For instance, to move the control room, to install a new correlator, where install it, etc. So there is a lot of projects that are coming. We are very excited about the future of all the things that we have in our hands here. And it's not, that's all. Any question?
Christian.
Yep.
Have a question?
Yeah. Hi, Christian and Nicolas. Good to see you again, guys.
Hi, great to see you. Nice to see you.
You guys mentioned you're gonna upgrade your link from Santiago to the site using the Reuna path.
Yes, right. The idea is, first of all, is to change the equipment because are obsolete. Probably they were obsolete when you were here. Now complete obsolete. So first of all, we will change the equipment for the new ones that will release some additional links. Okay. And after that, we expect to upgrade the link between the US to Santiago to at least 10 gigabit, probably more.
Right, and this is using the same path that you're using now, right?
The idea is to use the same path.
All right, cool. Thank you.
Welcome.
Okay, David.
Yeah, hi. Great to see you, Christian.
Hi, David.
Quick question about the The fiber optic from hell that you guys managed to get done with silica way back when that hit some problems with the gas pipeline. Is that all up, and have they given you the fiber swaps to get you redundant routes? What's an executive summary on that large amount of work you did?
There is several problems with we have several problems in the past with the fiber here locally in Santiago, especially in Santiago. We have a problem because the civil arrest. I don't know, probably you knew that happen sometimes in Santiago, okay?
Yes.
And unfortunately now a ring that is in place in Santiago, so that prevent that that happen as many times as in the past, okay? So that this is a very good news that happened a few months ago only, okay? But the ring is running. The problem now we have is with the main link to the north, okay? Yes. Because in that case, we have only one way, okay? And we are still waiting for an alternative until there. There was originally a plan, I don't know if you remember, to use silica to go through Argentina.
Yes, I remember that well.
But that didn't happen yet, and we don't have any news about that link, so we cannot wait for them. We need to find another solution.
That's fine. Okay, thanks for the update.
Albert, question?
Just a quick comment from my side. Actually, I'd like to take the opportunity to thank a lot Christian and Nicolas, because they help us a lot to set up one of our point of presence project. We did a simulation, and they provide all the hands and the equipment. So thanks a lot, guys, for all your help.
You're welcome. You're welcome.
Okay, any other questions for Christian or Nicolas? All right, we're doing very well with time. We actually have a little, we're early here. So the next speaker is for the Science Observatory. Simone?
I am
You
here.
ready?
Yeah, just
Okay.
give me a moment to try to share the screen. Give me
Okay.
1 second.
I can see it.
Trying to cut a little bit. Okay, you should be able to see the slide now.
Yes.
Okay. Yeah, I'm Simon Ayola. I work at the Center for Computational Astrophysics in New York, and I'm leading the data management effort for the Science Observatory. We've been presenting updates about the Science Observatory for the past 3 years. It's always a pleasure to be here, and I'll try to give you sort of the delta between 2021 and what has happened so far. And I do have a little summary of what the Science Observatory is in case there are new members that have just joined the group and they might want to hear more about it. As I mentioned, I'm part of the Science Observatory. I'm really presenting on behalf of many people across the globe that have put a lot of work in both developing software, but also building a new observatory in Chile. So here you see all of us, students, postdocs, and then professors at one of our last in-person collaboration meeting. I'm also very happy that this year, for the first time after COVID, let's say after COVID, that we're going to meet again in person in San Diego for another collaboration meeting. And this effort is currently funded by the Science Foundation and the Heising Science Foundation, so it's completely private. We do hope that funding agencies, especially in the US, will join our effort later on. We are a millimeter survey. I will give you a little bit more details about what kind of telescopes we have, but we basically divided the Science Observatory and the science reach of this observatory in two. One being driven by telescopes that can measure the large angular scales of the sky. So it's a low resolution survey that covers this patch that you see here from the Atacama Desert. And the idea here is to do high risk and high reward science. We really want to look for the signature of inflation, and the way you measure that through a millimeter sky is to look for the polarization imprint in this cosmic microwave background on large scales that supposedly will give, if inflation has happened, what we call a inflationary B-mode signal. This is very, it's a tiny signal to look for. We don't quite know the scale of such signal. And of course, we have things like the galaxy and dust that will creep in and will make this measurement even more difficult. So we are looking at the roughly 10% of the sky that we know. We have data knowing that it's low dust sky, and so hopefully the foregrounds will not will allow us to make a measurement if the signal is there. And then we have a completely different survey, a lot higher resolution, that covers roughly 50% of the sky, between 40 and 60% of the sky. It overlaps with the footprint that is the purpose of the Reuben Observatory, the LSST survey. And the idea there is to look at all sorts of science, going from primordial perturbation to relativistic species such as neutrino, and reionization, dark energy, and the transient universe that is becoming more and more important for the community, and very much highlighted by the decadal survey. And so, as I said, high resolution, very different survey. We cover a lot more of the sky, and we want to overlap with large-scale structure surveys to do some of this science. Although this is a privately funded project, we do plan to release these products to the community. We want this to be a project to be useful for the entire community. And so we do plan to release cosmic microwave background maps, but also derived maps such as lensing potential maps or sources and cluster catalogs, and of course, transients events. So we are developing a program that leads to delivery of high level science quality maps. And again, I want to stress the fact that we will be observing the same sky at the same time as the Reuben Observatory. So that's quite exciting for us for a lot of science. I don't need to tell you a lot about the site. Of course, we are in the Atacama Desert in Chile, and we really care about that because of we are a microwave experiment, as I mentioned, but also because we are targeting a very high sky fraction, and you really want to go in Chile to do that compared to the South Pole. Here's a rendering of the site. You might have heard or seen the ACT telescope. I'm also part of this project. Polar Bear and Sevens Array is here, class, and the Science Observatory will be joining the CMB effort on the plateau right here. And I'll show you a bit more of just the rendering. San Pedro de Atacama looks this way. We use it for line of sight connection. And of course, there is our partner ALMA. Let me give you an update on the site. If you've seen this presentation last year, as I said, I tried to give you a delta of what has happened. And a lot has happened at the site, of course, with all the delays that every project has. Now you can see that there are 3 fully realized platforms for the small aperture telescopes. I'll show you what those are in a second, but we have 3 small telescopes for those inflationary science that I mentioned. And here is where the large aperture telescope is going to be. And actually, this is a slightly outdated picture, because we already poured the foundation of the large aperture telescope. This is a 22 meter by 4 meter tall piece of concrete. It was poured in 2 different times, and each time took more than 30 trucks of concrete. So it was a huge project, which we finished. And here you can see the lab and the high bay that are coming together. So the foundations are there, the lab and the different containers are coming along, and we expect to be able to install computers and have internet connection at the site by summer of 2022. So soon we'll be able to communicate with the plateau. Connection that at this point, we're really thinking about a line of sight connection between the site and the low elevation facility in San Pedro de Atacama, as I mentioned. But I will mention about transmitting the data. What about the instrument briefly? If you haven't seen this before, as I mentioned, one large aperture telescope is a huge telescope, and with a 6 meter primary mirror. This design is very similar to the CCAT prime design that Michael will speak about later today. And there is a huge cryostat one of the biggest ever built for CMB observations that cools down detectors for our observations. And then we have three small aperture telescopes. There's much smaller telescopes. They are refractors instead of reflective, and they aim at those larger angular scales. So their design is meant to really reduce and control systematics at the hardware level before starting observations. We made a ton of progress on the hardware side. Last year, I showed you one of the platform being built and being tested in Germany. Now I'm happy to show you that all three are built and tested in Germany. And actually, an update to this, they've been shipped. So they are making their way to the site in Chile. Here you see more pictures of the construction of the large aperture telescope in Germany. Here you see the back structure of the panels. This is carbon fiber and part of the elevation structure, but also the 7 optics tubes that go inside the cryostat that will be basically the optics part before getting to the detectors. A lot of detector testing happening not only at the institutions that are developing the detectors, but also the different labs that are integrating. And here you see a picture of the integrated version of these detectors with all the readout for the small aperture telescope. So lots of progress. We are really in the interesting times of finishing the development and the integration to then slowly ship at the site to commission this neat observatory. I'll give you the timeline in a second for that, but I just wanted to mention sort of what data rates we expect. Our data rates are dominated by detector time streams. We don't have a lot of metadata and housekeeping data that is associated to it. And here we're talking about roughly 7,000 detectors that sample the sky at different rates depending on their observation frequency, but also whether or not they're mounted on larger aperture or small aperture telescopes. But roughly we're talking about 132 megabits per second. So it's not a huge data rate compared to some of the optical and bigger observatories, but is a lot higher than what is currently at the plateau, produced at the plateau. Here you can see a curve of detector counts and also the data rates as function of time as we go from commissioning to operation. At the current baseline for what the observatory is expected to be, we expect to have 3 petabytes of raw data over the 5-year survey that is planned for this observatory in a current state, and then there will be associated to that data products, science-ready data products that we would like to deliver to the public through different systems. Briefly, what's the timeline? Sometimes in the 2022, we expect first light for both the SAT and the LAT, so for both telescopes, in terms of having detectors mounted in a cryogenic system. We expect first science observations in early 2023, that's especially with the small aperture telescopes, to then finish this construction project in the mid-2024 and start the full operations, full science observations for the Science Observatory. And so here is the timeline that I mentioned. So this is a project that will be producing data and releasing data products to the public over 5 years. So we will go towards the 2030s. This is the overall project update, but let me give you a little bit more specific about what we do in data management and what are we dealing with right now. Data management pretty much covers the entire software development for the Science Observatory. We go from controlling and managing the daily observations at the observatory, so at the site, communicating the data, transporting the data, sorry, and communicating with the site from Chile to North America, having a software infrastructure that allows to simulate and reduce such data to then produce results and data products to the what we call the science analysis working groups. So we cover a big span of tasks, and we have a lot of deliverables here. Here, I just wanted to show you how such a final data product may look like. Here is a piece of a high resolution map from the ACT telescope. The LAT will look very much the same, where you can see the CMB at high resolution and a bunch of galaxies and clusters of galaxies in blue. This is a map at 150 gigahertz. So we expect very much similar data products, at least for the lab. Tomorrow will be for the SAT. So we've done this before, but the scale is much bigger, and so there are challenges there. On the data acquisition point, we have developed the observatory control system. Actually, the software is public. We try to put all our software public for any observatory to use. That actually was selected as a baseline plan also for the CMBS4 project. And right now we are using this software in SO labs for testing, and it will soon be deployed at the site as we start deployment. So this was a great success, and allows to really control the entire observatory and all the hardware subsystems that are present. Our relevance for this crew here, of course, we have a plan to transport the data from the high elevation facility down to well, all the way up, I should say, north to North America and possibly Europe. We do have a sneakernet plan, as David mentioned before. We have a way to transport disks if needed in case of emergency. And right now we will be using this plan until the point that the fiber link is fully developed. We do have a primary connection between the site all the way to San Diego. That's our primary path for data, and then we plan to sync the data and have 3 different copies at different centers. But also we would like to develop a secondary fiber link based connection path to sync the data NERSC in case this is not available. But this is basically how the simplified version of our topology of data flow looks like. And I'll come back to this in a minute. As I mentioned before, we have a unified framework with a lot of different pieces of pipeline and in our software stack. But basically, we want to support analysis that are that can be run on HPC systems. So we do not formally support high throughput computing, only high performance computing. And so NERSC and Princeton are the main facilities that will allow us to analyze the data. But before getting data, of course, we are moving forward with simulations. So we have fully developed pipeline for simulations, and we do plan to release publicly simulation data that the community can start looking at, so that they will have an understanding well before we start getting data of how our data sets looks like and what sorts of different analysis we can run. I wanted to mention that also these simulation data through DESK are sort of aligned with the Reuben Observatory observation. So we hope to do forecasting work based on SIMS well before both observatories start getting data. And then we have a pretty well developed pipeline for data analysis. Here I'm just showcasing some of the plots that amazing residents and postdocs make every day, mostly analyzing lab data, but also simulation. So we're really comfortable with the fact that this software is going to be working once we get to the site. So this was a brief update of where we stand. There is a lot more to develop. We're on an amazing track, but there is a lot more to develop before we start getting data and as we go through commissioning. But as far as the data is concerned, as the site comes up, we are implementing our connection design made of all fibers, of course, through the site to collect all the data that we need. This is something that pertains basically only SO. But here you can see that there is a router, and this router will allow us to connect to the ALMA infrastructure through to make sure that we can send the data and transfer data through a fiber link. You can also see that there is a microwave link that is supported, as I mentioned before. So Christian has said a lot of that. I wanted to mention that we are on board that plan, so we're going to be using it. The Parque Astronomico has constructed silica to lay a fiber that goes from the plateau all the way to the ALMA point of presence. As an update for this year, I wanted to mention that the silica project has been delayed a little bit, and so we expect to have that fiber available to us sometimes in the last quarter of this calendar year, which is totally fine, still totally within our plans for the Science Observatory. And to some extent, the Science Observatory will be managing or helping the other experiments that are currently there to connect to that fiber through that router that I mentioned. So this fiber hopefully will be available at the end of this year through Silica, and that will give us connection to the ALMA system. I don't need to add a lot more here, as Christian has said everything basically, but the idea is that through Reuna, we're writing an MOU with Reuna, and we'll be using their service to send the data from Cerro Taco with where the observatory is located all the way to North America, both NERSC and San Diego. So there is still a lot of discussion going on with Reuna to finalize the data path and sort of all the details of how the contract will take place over the 5 years of observations. And the Parque Astronomico is still in contact with Silica, who will be the provider of that physical fiber from the Cerro Taco to the ALMA point of presence. And that's pretty much the update I have, unless there are questions. I think I'm done. I'll leave it here.
Thank you, Simone. That was very nice. A lot of good detail there. And I see that you already changed the abbreviations for SAC in your slides. Very nice.
I tried. I might have missed someone, but I did try.
Yeah. Okay. Let's see. We have a question in the chat from Vasilka. Vasi, do you want to ask your question?
Well, I got the answer already. I just was wondering if you have an estimate about the data volume that you try to transfer to NERSC and University of San Diego. An estimate. Okay.
Yeah. So the daily data volume is about a few terabytes. It's not a huge data volume that we expect to transfer, and it would be continuous. So our current plan, our baseline is to have 2 copies at the site, immediate copies as the data gets registered on disks, and the data will be shipped to North America within 24 hours. The lag should be a lot smaller than that, as tests have shown, but we baseline 24 hours, and within the 24 hours, the data will also be moved around in the US. When 3 copies are fully realized in the US, the 2 copies at the site will be removed. So what I'm trying to mention is that the 24-hour amount of data that we want to move around, it's pretty small. We are talking about a few terabytes. On top of that, we might be moving data products as those become available, but again, that's of comparable size.
Okay, thank you very much.
Yeah.
Bob, you have a question?
Yeah, just a quick one. Thanks, Simone. That was a very nice talk. How, for someone who doesn't follow this wavelength too closely, how do I think of this in relationship to CMBS4 and what you'll do? Is it complementary or competitive or a little of both?
Well, let me say the timeline is different, as also the Decadal survey has highlighted. We place in between the stage 2 experiments, I guess, which are ACT, CLASS, and Polar Bear at the plateau, and CMBS4. So CMBS4 will start operations ideally after the SO project, the SO observation period is done. The Decadal survey has recognized that both the Science Observatory as well as the South Pole Observatory are precursors to S4, and so the community has suggested that we should use this observatory to really inform S4, both construction but also operation, and understanding what the science reach can be. Of course, S4 will have a lot more detectors, a lot more sensibility, so they will enable more science than what SO could enable. The science goals, the science topics are roughly similar. The goals will, of course, go deeper in terms of error bars on parameters and things like that. As a matter of fact, we're already collaborating with S4, and I'm very happy to see Eli at this call, because we have a monthly call between S4 and SO where we try to figure out all these connection and data flow questions together, especially using the amazing knowledge that the ES team has in NERSC.
Great.
So we're not in a competition. We are We're friends.
Yep, it's a staged.
Yeah.
Yeah. Yeah. Very good. Thank you.
Okay. Well, let's see. I have a note here from Vasi to remind people to upload your presentations. Make sure you do that, please, so that we can use